So let's start, Ehsan. So hello everyone. Today, Ehsan Shahoseini from Tarbiat, Modares University, Tehran will continue his presentation on deformation of Galois representation. Last week he spoke on the first part of this talk, and today he will complete his talks from last time. So Ehsan, you can start.
Thank you, Devendra. Yeah, today I want to discuss other things about deformation theory of Galois representation. Continue what we saw last week. Just remember that maybe most important thing, notation for today is GKS, which means absolute Galois group of KS, the Galois group of KS bar over K, where KS bar is maximal algebraic extension of K in K bar, which is unramified outside S. Just remember this. So, things. Yeah, we saw that we want to make the TD a K-vector space. TD was D of K epsilon for functor D from coefficient rings to sets. And before that, we discussed about Shahoseini criterion. We said that if D satisfies these four conditions, then D is representable. And this was the last thing that I said last week. Now, let's start with a new definition. We say that D is nearly representable if D satisfies just H1, H2, and H3. And this is important notion, as we will see in a couple of minutes. Let G satisfy the finiteness condition and let rho bar from G to G ln K be any representation, not necessarily absolutely irreducible. The proposition says that D rho bar, the deformation problem for rho bar is nearly representable. Then this deformation problem is nearly representable, and the important proposition says that if D is nearly representable, not necessarily representable, just nearly representable, then D of K epsilon has a natural K vector space structure, and it is finite. It is finite dimensional because of H3, because nearly representable means satisfying H1, H2, and H3. if we have such a diagram where A and B are equal to K epsilon and C equal to K, and we have this fiber product, we can define the addition map as follows. This addition map, since X and Y1 epsilon and X plus Y2 epsilon, both of these are X because they should have the same image in K. This is fiber product. So the first coordinate of them should be same. And we send this, we define this addition map to the X plus Y1 plus Y2 epsilon. And then use the functor D on this, apply D on this addition. So we have a map from D of K epsilon times K epsilon over K to D of K epsilon, which this map is the D of addition. And we know that by H2, because these nearly representable satisfies H2, and H2 says that H, and so H inverse is a bijection. So really this is equal to this left hand side, D of K epsilon times D of K epsilon, and we have fiber product. This is over D of K, but we know that D of K is a single one, so we don't write it. And we know that this is D of K epsilon is TD, and so this equal to this, and this equal to this, and by the functoriality of D, we have this addition property. So functoriality of D makes this addition here. So really we have a K vector space structure on TD for D nearly representable by this means. And corollary is that for the representation rho bar from G to GLN of K, where G satisfies P finite condition, T of rho bar, which by it means D of rho bar, is a K vector space, as D of rho bar is always nearly representable, and so as K vector space structure by what is as lines. But yeah, what is this tangent space? Let us study this tangent space in more detail. First, consider this remark that GLN of K acts by conjugation on Mn of K, and combine this action with this map rho from G to GLN of K. So we get an action of G on Mn of K. And by this action, we have that T of rho bar, the tangent space of rho bar, is isomorphic to H1 of G and M and K as a K vector space. This first cohomology group, cohomology of G with coefficients in M and of K, and action of G on M and of K comes from this remark. Let's make a short example, and we will work with this example in more detail in some minutes. Example is that let S consists of a single prime P, and we have a representation of GQS to GL2 of P such that it factors through S3, the symmetric group on 3 elements. And for example, we can construct these representations by these polynomials, as the splitting field of these polynomials is always 3, and yeah, by this condition, discriminant BP. So we want to we get a representation from GQS to S3. So the discriminant should be P. And for example, for A equal to -1, we get P equal to 23. I would say about P equal to 23. And the point is that the universal deformation ring for this representation is ZP adjoining 3 variable, this power series ring. This is a huge ring. For example, you can specialize to get many other deformations. For example, if you specialize x1, x2, and x3 by elements of PZP, elements of maximal ideals, then this power series, for example, converge to an element of ZP, and you get a representation, you get a deformation into GL2 of ZP, for example. Or, for example, if you just specialize at some point for x1, then you get a deformation into a 2 variable power series over ZP. What we have seen was the absolute theory, and we have a relative theory too. For relative theory, we start with the deformation of rho bar, and we start with a representation rho bar, and we consider a deformation of it where rho bar goes to GLN of A, such that A is a coefficient ring. And really, deformations, if you remember, was strict equivalence classes of liftings, but you consider a representative of that strict equivalence class. Really, rho is an actual homomorphism, not a strict equivalence class, a representative element of that strict equivalence class. And relative deformation problem is as follows. The functor d rho, we write d rho instead of d rho bar, from the category of coefficient rings with residue field K and with A augmentation. By A augmentation, we mean a map to A. All coefficient rings A1 with a map to A. We call it with A augmentation. And this goes to the category of sets such that this A1 that has a map to A goes to deformation of rho to A1. Not only deformations of rho bar, but deformations of rho to A1. And like the absolute case, we can define the tangential space. The tangential space defines as this d rho t rho, which is t of d rho, real defines as d rho of k epsilon, such that epsilon square is 0. And like the above proposition, we have this isomorphism known as A modules, that this tangential space is isomorphic to first cohomology group of G with coefficients in Mn of A, and the action of G on Mn of K really is like above. GLN of A acts on Mn of A by conjugation, and we have a map from G to GLN of A. So combining these two things to get an action of G on Mn of A. Let's go to another topic. neotropic conditions on deformations, which is very important because many times we want to study deformations with some extra conditions. For example, representations that arise from elliptic curves or modular forms satisfy these. For example, we say that representations that arise from elliptic curves have determinant cyclotomic, has the determinant as cyclotomic character, and some other conditions also, not just this. So we have some conditions, and we want to study this type of deformations. The first condition that we want to study, and we go through some details for that, is fixed determinant condition. I write quotation here because it is really, in some sense, has a different meaning with the usual notion of have some determinant, because you can make a map from here to A star with determinant, and but this determinant condition is not the same as this determinant, the usual determinant. So I use quotation determinant. We have the representation G goes representation rho from G to GLN of A, and we have also residual representation rho bar from G to GLN of K. And we are given the continuous character delta from G to GLN of WK star, where WK is the ring of Witt vectors. But you can think about it just as really, you can think about this just as ZP if you are not familiar with vectors. Just you can consider ZP star, not important really. It's enough to think about ZP star. We say that the representation rho has the quotation determinant delta if the following diagram be commutative. We have this diagram where this map is rho. This map is the usual determinant. The usual determinant is this map. This map is delta, our character, and this map is really A. If A has residue field K, then always we have a map from Witt vectors of K to A. So we have a map from units of this to units of this. But always, as I said, we can consider ZP because always ZP star is the subring of this. So we have this. So it's enough to work with ZP. And we want this diagram to be commutative. In other words, IA times delta, IAO delta B determinant of rho. If this satisfies, we say that the representation rho has determinant delta. And we can impose this condition on our deformation problem. Note that rho bar has determinant delta too. We can consider our deformation problem was d rho bar, and we write the functor d rho bar and delta. This functor from category of coefficient rings with residue field K to set, that sends a coefficient ring A to deformations of rho bar with determinant delta, with quotation determinant delta. So consider this is a subfunctor of the rho bar. Trivially, this is a subfunctor, as the rho bar and delta of any A is a subset of the rho bar of A. So it is a subfunctor. And note that the little k goes to singleton row bar. I mean, it is not empty. We know that the row bar of k also is a singleton, but note that the row bar delta of k is also a singleton, is not empty. And the point is that the row bar and delta, this functor, which is a subfunctor of the row bar, is nearly representable. And also, if row bar be absolutely irreducible, then it is representable. As we see that, as we saw that, really, this was true for the row itself, that it was always nearly representable, and if row be absolutely irreducible, then it was representable. This also holds for the row bar and delta, and we will see that this is true for all conditions, not just the condition of having a fixed determinant delta. This will be true for all conditions. We will see this. And because of being nearly representable, we have a natural k-vector space structure on the tangent space of d row bar and delta. So we can study this tangent space. T of the row bar and delta, which we write it as T of row bar and delta, where we know that this is d of row bar and delta of k epsilon really. This injects into T of row bar. This is a subspace, as it is T of row bar is equal to d of row bar of k epsilon, and we know that d of row bar and delta is a subfunctor of d of row bar, so this is just a subset. And we saw that this is isomorphic to this cohomology group. So really, there is a subgroup of this cohomology group. This is just a notation. This is just, there is a subgroup of this cohomology group. I write it H1 sub delta of G and M and K. That should be isomorphic to this tangent space. If this has a subgroup, that should be isomorphic to this, and I write it as H1 delta of G and M and K. I write here delta as fixing the determinant delta. Having determinant delta is our deformation condition. And this lemma says to us that really this subgroup H1 delta of G and M and K is really a cohomology group again. It is H1 of G and M and of K node, where by this node we mean, by M and of K node we mean the trace zero matrices. M and of K node is matrices in M and of K such that they have the trace is equal to 0. And the point is that these trace zero matrices are G stable, so we can define this cohomology group. So nicely, this subgroup really is of the form of a cohomology group again. And let's go to the above example in more detail. For S equal to P, single prime P, and this representation GQS goes to GL of P that factors through 3. Let's consider some conditions on deformation and study say something about, at least not study, say some few facts about universal deformation rings. If we impose no condition, let D0 be no condition, then universal deformation rings, we saw that is the ZP adjoining 3 variable, power series string with 3 variable over ZP, if let D1 be representation with some fixed determinant, quotation determinant, then universal deformation ring of this D1 really is a quotient of universal deformation ring of D0 is a quotient. There is a surjective map here, and just really the quotient is taking mod one variable, so it remains 2 variables for us, the P of x1 and x2. And if we impose another condition, let D2 be the condition D1 fixing some determinant plus this condition that rho P from rho P, which is the restriction of rho to GP, goes from GP to matrices of this form, this element B0. And because just P is ramified, S equal to P, just we need to impose the condition for P. And then again, this universal deformation ring of D2 is the quotient of universal deformation ring of D1. And again, we lost one variable. Universal deformation ring of D2 is P of x, one variable. And if we impose another condition, D3, let D3 be D2 plus the condition that if
Hello, Ehsan, your voice is lost. Ehsan. Hello.
sorry, I had no connection for, I don't know, for some seconds or minutes. Do you hear me now?
Yeah, it is clear now.
Yeah, thank you. I say something about these conditions. Do you hear my explanation about the D1 or D2 or what? Sorry, D1.
Yeah.
Yeah.
So from the
did
second
you
last row, yeah, second last row. Yeah, this one.
Second. Okay. Okay. Yeah. If we let D2 be the condition, D1 having fixed determinant plus plus the condition that restriction of rho to GP be restriction of rho to GP sends GP to matrices of this form star star 0 star, then our deformation ring is isomorphic to ZPX, we lost another variable. And if D3 be D2 plus restriction of rho rho p, that's restriction of rho p to inertia group be such that sending inertia group to matrices of this form, then we have these matrices. We have this deformation, universal deformation ring. It is just ZP, so there is a unique lifting to ZP, really. This is nice. And in some sense, this is a full set of conditions. We start with a big ring, big universal deformation ring, and we impose some conditions in some steps, and we get just ZP at the end. Note that, for example, if when p equal to 23, that we have seen above t, and let the quotation determinant be 11th power of cyclotomic character, chi6, then the universal deformation to GL2 of ZP that we get by D3 is really the representation attached to modular form of weight 12 delta, the Ramanujan delta function for the prime 23. So these representations occur in practice. Now let's say something about general conditions on deformations problems for rho bar. We have, for example, stated fixing some determinant condition and can impose other conditions. But first, what we mean by a condition. Okay. Deformation problem is packaged by its functor, the rho bar, and the condition will be just a subfunctor, the tilde of the rho bar that sends A to the tilde of A, which is a subset of the rho bar of A, just like deformation with fixed determinant. And we have two requirements. The first one is that the tilde of little k is non-empty, so it is just rho bar. And another one is that the tilde in the rho bar be relatively representable. I want to define it now. The tilde in the rho bar be relatively representable. What means? So we have this definition. The tilde in D is relatively representable if for all diagrams of coefficient rings A and B goes to C with residual field K, this diagram be Cartesian. This diagram that goes from D tilde of A times B over C to D tilde of A times D tilde of B over C, and this goes and the bottom you should write D instead of D tilde. We have seen that representability implies that this map and this map are bijections, but relative representability just means the Cartesianness of this diagram, and is about two functors relative representativity. And an important remark is that if the tilde in D is relatively representable, then if D satisfy HI for each I, for example, if D satisfy H2, by HI, I mean Shahoseini conditions, H1, H2, H3, and H4, D satisfy each of HIs, then the tilde also satisfies. And in particular, if D is nearly representable or representable, nearly representable means satisfies H1, H1, H3, and representable means satisfies H1 to H4, all of them. Then the tilde is 2. So, in particular, every condition is nearly representable as the rho bar is always nearly representable. And if rho bar be absolutely irreducible, then this condition is representable really as the rho bar is represented. So because of this near representability, we have always the condition, every condition is nearly representable, so we can speak about tangent spaces. And tangent spaces for conditions, we study them. We have the condition detailed in the rho bar. Then T of detailed, which is a k-vector space because of its near representability, is a subset of T of D rho bar. And we know that this is isomorphic to this cohomology group. So as this is a subset, this should be isomorphic. This should be isomorphic to a subset of this cohomology group, to a subgroup of this cohomology group. But yeah, just we write this. This is just a notation. This may not be a cohomology group really. This is just a notation for a subgroup of this cohomology group. We write this subgroup that is isomorphic to TD tilde as H1 D tilde of G and M and K. Now, we have this. We want to discuss about local and global deformation conditions. Let G be equal to GQS, and we have the residual representation rho bar to GL2 of K, or maybe GLN of K. Nothing important. This is not important really. This can be any N. And let's restrict this this rho bar to GL. So rho bar L is the restriction of rho to GL. We have this commutative diagram. We impose a system of conditions on this diagram. Let's first fix a character delta from GQS to WK star, or simply ZP star. And by this we mean fixing a quotation determinant delta to fix this condition. And the second one is fix a condition DL tilde in D of rho L bar. We have a deformation problem for rho L bar because we have this map. So we have a deformation problem here. D of rho L bar, and we fix a condition D tilde L for each L in S for ramified primes. And we call them local condition at L. And we call this all conditions together is having this determinant and all local conditions together. We call them D tilde and we name it global condition. By a D tilde deformation of rho, we mean let D tilde is a we know that rho bar is a global. Rho bar is from GQS to GLN of K, so it is really a global representation. And deformation of this detail, which is a global condition. By a detailed deformation of rho bar, we mean a functor detail that satisfies this property. This diagram be Cartesian, if this diagram be Cartesian for any coefficient ring A with residual field K, then we say that D field is a D-deformation of rho bar. It means really that an element of D field of A is a deformation of rho bar with which determinant delta is an element of here, such that when we map it to local conditions, local deformation problems, it comes from local conditions that we impose. We impose here. Being Cartesian means this. And lemma says that detailed this global condition, this global condition is really a condition. Detailed in the rho bar is really a condition. It means that it is it means that remember that it means d field of A is singleton rho bar, and d field in the rho bar is relatively representable. This is the definition of being a condition. Now let's interpret this diagram in terms of tangential spaces. And it's enough to apply the above diagram to A equal K epsilon, as D of K epsilon is the tangential space. So, for example, here D tilde of instead of A, right? K epsilon take us T of D tilde. Now we have this T of D tilde, and here the tangential space of this, the tangential space of this, we know that it is isomorphic to cohomology group of G, our group GQS, with coefficients in traceless matrices with trace 0. And for these two things, for example, we know that it is isomorphic to cohomology of GL with coefficient in Mn of A. That's this, and we write here this notation, H1 D tilde L. This is just a notation. This is just a subgroup of this cohomology group, which is the analog of this here when apply this DL to K epsilon. And we have this diagram, this commutative diagram. And note that if we let rho bar be absolutely irreducible, then the rho bar and so D field are representable. For example, D rho bar is representable by R unique, universal deformation ring. We call it R unique, which is R rho bar, universal deformation ring. And D tilde is representable by a ring R unique. D tilde, which is a quotient of R unique, is this surjective map. Universal for detailed deformation. And this, in this case, in the representable case, is T of detail as a simple interpretation. Really, T of detail is nothing other than T of R universal detail, tangential space of this universal deformation ring in the representable case. What I said until now was for absolute theory, just for raw bar. Let's move to relative theory. For relative theory, we need to work with Taylor differentials. Let R be any coefficient ring, and for simplicity, let little k, our residual field, be Fp. We can work with general residual fields, but with more notations and more tensor products. So for simplicity, that just I write Kb equal to Fp. We have this map from R tensor R over from now on, all tensor products are over Zp, and I skip this notation. I just write tensor like this, but by tensor I mean tensor over Zp. Let's call this map R tensor R to R, which sends A tensor B to AB, the product map. Call it alpha, this is a surjective map, and call its kernel I. We have this exact sequence. The point is that we need completed tensor product, this notation is completed tensor product, because we want to be in the category of coefficient rings, and category of coefficient rings is not closed under usual tensor product, but it is closed under the completed tensor product. We get the completion. For example, I can define it one line. We know that R is complete, so R is isomorphic to the inverse limit of Rn, and R completed tensor product R is just inverse limit of Rn tensor Rn. Or you can define in another way. For example, you can define it in another way. R tensor R goes to R by the product. It is not complete. There is a kernel here. Write it M. There is a. This is a sorry. This is a local ring. This is a local ring. Have a maximal ideal M. R tensor R, and it has a maximal ideal M, and now complete this ring. Now complete this ring R tensor R with it with respect to its maximal ideal, and yeah, it is the completed tensor product. Okay. We know that I is the kernel, so I is I is an ideal of this ring, so I is an R tensor R module, so I mod I squared is an R tensor R over I module, but we know that R tensor R over I by this exact sequence is isomorphic to R. So really, I mod I squared is an R module, and we define the Taylor differential omega R to be I mod I squared. The proposition is that for the absolute case, R module homomorphisms from omega R to little k is nothing other than TR, the tangential space to R. And we use this analogy for the relative case. We introduce the relative theory in terms of omega R. We use this, we use this equality, this isomorphism to write the tangential space in this form for the relative theory. We have this diagram, this commutative diagram, the residual representation from GQS to GLN of K, where rho bar is absolutely irreducible, and we have a deformation of rho bar, rho to GLN of A, which is really a representative element of the deformation. It's not an strict equivalence class, it is a real homomorphism. Let D tilde be a condition, and let rho be a D-deformation. As rho bar is absolutely irreducible, we have seen that R universal D tilde, we have seen that D tilde is representable because of absolute irreducibility. So there is a universal deformation ring for D tilde or unit D tilde, and because of this condition, rho is D tilde deformation. So there is a unique map from R universal D tilde to A. So A is R universal D tilde algebra. For a study the tangent space, in this case, we need to specialize to two cases. The first one, let A, this A here, be Artinian, or equivalently in this our setting, be finite. Artinian coefficient rings are the same as finite rings. The coefficient rings that are Artinian are finite. And proposition says that it is very look-like to look at this proposition in some second. Look at these three things. Really, these are the same as absolute theory. H1 of GQS with coefficients in traceless matrices, and this product and this product. Just here we have TD, and in the relative theory we use the Taylor differentials. So here the proposition says that this diagram is Cartesian. Here we have H1 of GQ and Mn of A naught, GQS and Mn. And here this is this product of homology group, and here is this subset of homology group that we use this notation for it. And this is our tangent space, which is our D tilde modules, our universal D tilde module homomorphisms from omega of R D tilde universal to A. And by Cartesian, it means that given an element here, it is enough to give an element here when we map it to this these restrictions, restrict to local counterparts. They comes from these conditions DL that we impose on our deformation. The second case is that AB free over ZP, and the diagram is the same, except these coefficients should change very slightly. Just proposition said that this diagram is commutative, and you said that just coefficients tensor with QP over ZP, tensor over ZP, again said tensor over ZP. And I have not write any tensor here. Tensor always is over, I write here for, say again, tensor over ZP. Everything is the same as above, but coefficients are changed by tensoring them with QP over ZP. No other thing is new. The point is that here we work with traceless matrices. Now let A be equal to ZP. We can work with more general ring of integers of local fields, but for simplicity, let's work with ZP. And there is a surjective map from our universal of detail to ZP, which is A. We call it beta. And the kernel of beta, we call it P. It is a prime ideal because ZP is an integral domain. And we have this exact sequence. And the fact is that it is really very look like to the definition of Taylor differentials. This omega of universal deformation ring of detail tensor with ZP over universal tensor over universal deformation ring of detail is isomorphic P modulo P squared. And also this is nothing other than this. We want to change this. This homomorphism from omega of universal deformation ring of detail to A tensor Q is that over ZP is nothing other than A module homomorphisms from omega of universal deformation ring of detail tensor with A tensor over universal deformation ring of detail to the same thing, A tensor QP over Z. So here we tensor with A over universal deformation ring of detailed, and coefficients change from R detailed module homomorphism to A module homomorphisms. Now use this with the case that AB ZP, AB equal to ZP, and use this fact which this P over P squared by that fact, and rewrite this diagram. We get new proposition that this diagram is Cartesian, and this is just above diagram. Here A is ZP, no general A is ZP, and here use that fact, P mod P square appears. Oh, time is up, and also my notes is up.
Are you
I have
done?
no other thing to say.
So actually, if you could briefly tell the starting point of the deformation theory of Galois representation in this Fermat-Last theorem or the modularity theorem, how it comes to use or application.
Yeah, really, before I just want to mention my reference. I use just one reference there are more other nice references. I just used this book, which is a very huge book, about 400 or 600 pages book,
Is
modular
that
forms and Fermat-Last theorem, edited by Cornell, Silverman, and Stevens, which
yeah, well,
contains the proof of Fermat-Last theorem. I used the chapter 8 of this book. It's about 70 pages and written by theorician of deformation theory, Barry Mazur. I choose this because I really don't know the proof of Wild's theorem of modularity and how really this deformation theory uses for proof of modularity. But surely, I'm sure that what I said used for proof of modularity, as Barry Mazur says these things for preparation to the proof of modularity.
yeah, certainly. I think we are understand that it is used in that theorem, proof of that theorem, or maybe later that BCDT theorem. But exactly where it is required, like we have to show that a Galois representation is modular,
I think, yeah,
and
I
it means
think,
that it comes from some modular forms.
yeah.
So
I'm not sure, but I think because there is another nice reference for deformation theory. The lectures by Professor Shonak Do in an event of ICTS.
I
Uh,
see.
right, ICTS 2021. Maybe elliptic curves and special values of
Yeah, it happened last year. Yeah.
like
So
that.
how many talks
Professor
are
Shonak
there?
speaks about Galois. Yeah.
How many talks he gave there
Uh,
on this
I
topic?
think I think Professor Shonakyo had 5 talks on Galois representations, and at least 3 of them about deformation theory. And in the last talk, in the last of his talks, he says something about R, the philosophy of R equal to T. This is
I see.
universal deformation ring of Galois representation, and this is universal deformation ring, and this is a localized Hecke ring. And one main point of deformation theory, I think, is for proving R equal, is for constructing this ring and using techniques of for proving this equality. I think it is based on commutative algebra techniques. But for construction of this universal deformation ring, we need deformation theory of Galois representations attached to elliptic curves and attached to modular form. I'm not sure completely, but I think universal deformations appear in this context.
This came in the Anwes talk also. Our
Sorry, what?
CVH. This R equal to T came into the Anwes talk, second talk of this semester.
Yeah. I
There's
remember.
the Taylor-Wiles method.
Yes. But it is more. I think it is a combination of. For proving R equal T, we need a combination of commutative algebra techniques for proving ring isomorphism and a study of universal deformation rings, because R is itself a universal deformation ring, and T is we have a Hecke algebra, and we have a Hecke algebra, call it T1. Let me call it T tilde, and we localize it at some maximal ideal, and this is a local ring T, and we have a universal deformation ring, and we should say that these are isomorphic. These are isomorphic to other. Really, I think the deformation theory appears in this way for proving modularity, but I don't know the details, the exact meaning of how really one should use in detail the deformation theory for proof of modularity.
Yeah,
but
it's okay.
But surely it contains in this book, this huge book.
Yeah, I have seen that. Yeah.
It is very nice book. I just read one chapter. This chapter is in some sense a huge chapter, 70 pages. But
Was
very
it
well.
possible to read this chapter independently? What was your prerequisite to read that chapter?
Yeah, you can read it. It is not really dependent to any other chapters, because many of chapters, I think chapters 1 until chapter 1 is an overview of Wald's proof in maybe 10 pages. So you can skip it, and chapters 2 until chapter 9, maybe, or until chapter 8, are really independent of each other. All of them are in some sense introductory chapters, one about elliptic curves, one about modular forms, one about Galois cohomology, finite flat group schemes, modularity of triadic representations, mod 3 representations of elliptic curves, an overview of third conjecture, and introduction to deformation theory. These are chapters 2 to 8. And chapter 9 is also an explicit construction of universal deformation ring. These are, in some sense, introductory chapters. And I think from chapter 10, the main parts of proof starts with Gornstein property and Pecke algebra and some other things. So I think you can read any of chapters from chapter 2 to chapter 8 independent of each other.
I see. Thanks for this very robust talk about deformation theory. I think it would be useful for anyone who would like to verify details. Harsa, you have any questions?
No. Thanks for the talk. It was very good.
Yeah, okay, then we can leave this meeting, Ehsan. By the way, can you stop the recording? Bedehi, are you there?
Yeah. I'll stop it.
Okay.